The law of quadratic reciprocity holds a special place in the theory of numbers. Its importance is so highly elevated that one could view it as the ultimate object of studying number theory in the first place. Despite this concept hasn't acquired the same level of popularity as some of the other mathematical discoveries of equal footing. Maybe this could be owed to the fact that explaining it in concise terms without any prior knowledge of number theory can sometimes be viewed as hard. But whatever be the reason, it is time to amend this. This three-part series of videos will serve as a complete exposition of the law of quadratic reciprocity. The first two parts will explain the associated theorems required to understand the law of quadratic reciprocity, along with their respective proofs. The third video will give the statement of the law itself, along with its own proof, and will then end with a short example showing the law in use. In addition to compiling all three videos into a single playlist, the links to the other two videos in the series are provided in the description. This video concerns Euler's criterion and the introduction of the Legendre symbol. We start with the concept of quadratic residues and non-residues. Just to refresh your memory, let me call your attention to the fact that in the notation of modular arithmetic, the symbol A congruent to B mod n signifies that A and B leave the same remainder on division by n. The solution of quadratic congruences lies at the heart of quadratic reciprocity. If the congruence x square congruent to A mod P is solvable for a given value of A with P an odd prime, then we say that A is a quadratic residue modulo P. Note that in most of the subsequent discussions, whenever we mention a prime P, we are only considering odd primes. Now, if the congruence doesn't admit a solution for a given A, then A is termed as a quadratic non-residue modulo P. What's more is that we can further simplify our study of the equation by eliminating all cases when P divides A, because those lead to the trivial solution x congruent to 0 mod P. The reasoning is simple. P divides x squared minus A, as A and x squared leave identical remainders on division by P. This, in conjunction with the fact that P divides A, implies that P divides x squared, and so x is congruent to 0 mod P. When P doesn't divide A, then the GCD of A and P is 1. Next, we establish Euler's criterion, which gives us a means of determining which values of A are quadratic residues modulo P. Firstly, the statement of the criterion is as follows. A number A is a quadratic residue modulo P, where P is an odd prime if and only if A to the power P minus 1 upon 2 is congruent to 1 modulo P. The proof is elementary. If A to the power P minus 1 upon 2 is congruent to 1 mod P, then we select a primitive root R of P. We know that there exists a number K between 1 and P minus 1 inclusive, such that R to the power K is congruent to A mod P, where K is the order of A with respect to R. Furthermore, R to the power K raised to the power P minus 1 upon 2 is congruent to 1 mod P. But we also know that P minus 1 divides K into P minus 1 upon 2, as P minus 1 is the order of R. This quickly leads to the result that 2 divides K. In other words, K is equal to 2J. Hence, R to the power J is a solution to the quadratic congruence x squared is congruent to A mod P, since R to the power J squared is congruent to A mod P. So, if A to the power P minus 1 upon 2 is congruent to 1 mod P, then A is a quadratic residue. For the opposite direction, if A is a quadratic residue and x naught squared is congruent to A mod P, then A to the power P minus 1 upon 2 is congruent to x naught squared to the power P minus 1 upon 2, which is congruent to x naught to the power P minus 1 modulo P. But Fermat's theorem tells us that x naught to the power P minus 1 is congruent to 1 mod P, since x0 and A are coprime to P. Finally, we get that A to the power P minus 1 upon 2 is congruent to 1 mod P, which confirms the criterion. The next tool we make use of concerns quadratic non-residues. Again, we limit our attention to odd primes only. If the GCD of A and P is 1, Fermat's theorem dictates that A to the power P minus 1 is congruent to 1 mod P. This can then be factored to give A to the power P minus 1 upon 2 minus 1 into a to the power p minus 1 upon 2 plus 1 is congruent to 0 mod p, as p minus 1 upon 2 is a whole number. If a is a non-residue, then p doesn't divide a to the power p minus 1 upon 2 minus 1. Hence, p divides a to the power p minus 1 upon 2 plus 1. This yields that for all non-residues, a to the power p minus 1 upon 2 is congruent to negative 1 mod p for odd primes p. Notice how for quadratic residues, the congruence a to the power p minus 1 upon 2 congruent to negative 1 mod p is not satisfied. If it were, then we would have that 1 is congruent to negative 1 mod p, leading to the contradiction that p divides 2. Proceeding further, we now introduce the concept of the Legendre symbol and discuss its properties. Again, we assume that p doesn't divide a and p is an odd prime. The Legendre symbol a upon p has the following definition. A upon p equals 1 if a is a quadratic residue of p and equals negative 1 if a is a quadratic non-residue of p. Now for its properties, we make the assumption that the two numbers a and b are both coprime to p. If a is congruent to b mod p, then the Legendre symbol a upon p equals the Legendre symbol b upon p. Obviously, if the equation x square congruent to a mod p has a solution, then x square congruent to b mod p also has a solution, since a is congruent to b mod p. What's more is that they have the same two incongruent solutions modulo p. But if one of them is insolvable, then so is the other. 2. A squared upon p equals 1. This is straightforward since the congruence x squared congruent to a squared mod p is satisfied by a itself. 3. A upon p is congruent to a to the power p minus 1 upon 2 mod p. This third statement is a rehashed version of Euler's criterion for residues and non-residues. If a is a quadratic residue, then we have a to the power p minus 1 upon 2 is congruent to 1 mod p, and if it is a non-residue, then a to the power p minus 1 upon 2 is congruent to negative 1 mod p. Surely 1 is not congruent to negative 1 mod p because p doesn't divide 2, so we don't have to worry about cases that are mixtures of these two, as none such exist. 4. AB upon p equals a upon p into b upon p. We now resort to statement 3 to prove statement 4. AB upon p is congruent to ab to the power p minus 1 upon 2, which is congruent to a to the power p minus 1 upon 2 into b to the power p minus 1 upon 2, which is congruent to a upon p into b upon p mod p. But the congruence is in fact an equality in this case. The Legendre symbol can only take on the values 1 and negative 1. So if ab upon p is not equal to a upon p into b upon p, then it must be the case that one is plus 1 and the other is negative 1. But once more, this is absurd in lieu of the fact that p doesn't divide 2. 5. 1 upon p equals 1 and negative 1 upon p equals negative 1 to the power p minus 1 upon 2. Here we can simply apply that which we have already learnt. 1 upon p equals 1 squared upon p, which equals 1. And negative 1 upon p is congruent to negative 1 to the power p minus 1 upon 2 mod p, which translates to an equality for the same reason as mentioned before. 6. ab squared upon p equals a upon p. Here we just fall back on statements 2 and 4. First applying 4, we have that ab squared upon p equals a upon p times b squared upon p. But b squared upon p equals 1, so that ab squared upon p equals a upon p. With Euler's criterion being proven and the properties of the Legendre symbol elaborated upon, the first of this 3-part series of videos ends. Thank you for watching, and I hope to see you in the next video where we discuss Gauss's lemma and an extension to it based upon the same principles. So that's all for now. As a short postscript, please note that all the credit for the proofs and theory goes to David M. Burton, who is the author of the book Elementary Number Theory. In addition, credit is given to McGraw-Hill Education India Private Limited, who have published the Indian edition.